Astronomers are observing the oldest light in the universe, known as the cosmic microwave background radiation, thanks to a combination of advanced technology and strategic observational techniques. This relic radiation is the afterglow of the Big Bang, dating to about 380,000 years after the event when the universe cooled enough for atoms to begin forming and photons to travel freely. The detection of this ancient radiation has provided invaluable insights into the early universe. Astronomers use specialized satellites and telescopes designed to detect microwave waves to observe this faint radiation. One of the most significant missions in this area was the Wilkinson Microwave Anisotropy Probe, which mapped temperature variations across the sky, revealing tiny variations in the intensity of the cosmic microwave background. Another landmark mission, the Planck satellite, has further refined these measurements and provided a more accurate understanding of the composition, shape, and age of the universe by obtaining detailed images of the cosmic microwave background. Observations are made from high altitudes or from space to avoid interference from Earth's atmosphere, which can distort or absorb microwave signals. These instruments are often equipped with sensitive detectors capable of picking up minute differences in the temperature and polarization of the cosmic microwave background, allowing scientists to study the physical underpinnings of the early universe and its expansion. These observations have emphasized several crucial aspects of cosmology, such as confirming that the universe is flat and providing evidence for the existence of dark matter and dark energy. In addition, analyzing the cosmic microwave background has yielded a wealth of data that helps us understand the evolution of the universe and make discoveries about its large-scale structure and the processes that have governed its expansion and development over billions of years. By meticulously studying this ancient light, astronomers continue to unravel the tangled history of the universe itself. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, is a revolutionary facility designed to detect and measure gravitational waves, ripples in space-time caused by some of the most violent and energetic processes in the universe, such as the merging of black holes or neutron stars. LIGO consists of two observatories, located in Washington and Louisiana, that work in unison to pinpoint the source of gravitational waves by measuring minute changes in the distances between suspended mirrors separated by 4 kilometers. LIGO's contribution goes far beyond simply detecting these ripples. Gravitational waves arising from cosmic events carry invaluable information about their origin. By analyzing the properties of these waves, scientists can reveal details about the nature of the objects involved in their formation, such as the masses and spins of colliding black holes or neutron stars. These data enrich our understanding of stellar evolution, the behavior of extreme matter, and the fundamental laws of physics. Although LIGO primarily detects phenomena occurring in the universe today, its observations are important to our understanding of the early universe. Gravitational waves can serve as a tool to study conditions after the Big Bang. Theoretical models suggest that there were significant gravitational waves in the early universe, especially during events such as cosmic inflation, the rapid expansion that occurred immediately after the Big Bang. By studying gravitational waves, scientists can indirectly learn details about inflationary scenarios, the state of the universe at the time, and even the formation of primordial structures. In addition, the LIGO discoveries have paved the way for a new field known as gravitational wave astronomy. This emerging discipline promises a multi-messenger approach to studying the universe, combining observations of gravitational waves with electromagnetic data from traditional telescopes. Together, these techniques provide a more complete picture of cosmic events and contribute to a better understanding of the fundamental processes that have shaped the cosmos from its earliest moments to the present day. As LIGO continues and new facilities become available, the data will undoubtedly refine our interpretation of the history of the universe and its underlying physical principles. Space telescopes like the James Webb Space Telescope play a vital role in allowing scientists to peer into the past by observing light as it travels vast distances across the universe. When we look at distant objects like galaxies or stars, we don't just see them as they are today. We observe their light as it was when it was created. This means that when we study very distant celestial bodies, we are peering into the past, allowing researchers to gain insight into the history and evolution of the universe. The James Webb Space Telescope is particularly adept at observing infrared light, which is essential for studying objects at great distances. As the Moon moves through the universe, a phenomenon known as redshift occurs. This effect stretches the wavelength of light, turning it into infrared radiation. Many of the first stars and galaxies formed during the so-called cosmic dawn, which occurred shortly after the Big Bang. Their light, which emits a red color outside the visible spectrum, is most visible in the infrared. The James Webb Telescope can collect this infrared light and reveal information about structures in the ancient world that were previously hidden. With advanced instruments, James Webb can analyze the characteristics of this light, allowing scientists to study not only the composition and temperature of these distant objects, but also the history of their formation and evolution. For example, researchers can study how galaxies merged and evolved, leading to the structures we see today. With these capabilities, James Webb can compile a detailed chronology of cosmic events, shedding light on crucial moments in the history of the universe. In addition, studying the light from distant stars provides information about the formation of elements and conditions that existed in the early universe. By measuring light from ancient celestial bodies, the James Webb can reveal the processes that governed the synthesis of elements after the Big Bang, thereby furthering our understanding of the formation of stars and galaxies. So, the James Webb Space Telescope acts as a powerful time machine, revealing the secrets of the universe's past and helping us understand its past and future. Redshift is a phenomenon that occurs when light from an object in space is stretched to longer wavelengths as it travels through the universe. When an object moves away from the observer, the wavelengths of light emitted become longer and shift to the red part of the energy spectrum, hence the term infrared. This effect can be set to the sound of a passing train. The train moved on, and the sound became quieter. Similarly, the farther light travels, especially from distant galaxies, the longer the wavelength. Redshift is an important tool for astronomers not only as an indicator of motion, but also as an indicator of the expansion of the universe. By measuring the redshift of light from distant galaxies, scientists can determine how fast these galaxies are moving away from us. This measurement allows us to calculate the speed of the galaxy, and for astronomers to understand the dynamics of the expansion of the universe. Edwin Hubble's observations of redshifts in the early 1900s revealed the vastness of the universe and laid the foundation for modern astronomy. Redshift not only tells us about the expansion of the universe, but also plays an important role in calculating the age of the universe. Because galaxies have been emitting light for billions of years, the light we see today contains information about its journey through time and space. By analyzing the characteristics of the Moon in ancient galaxies, astronomers can determine how much time has passed since the Moon came to us and determine when it first appeared. The higher the redshift, the greater the distance and the older the galaxy. Scientists can create a timeline of the history of the universe. In addition, redshifts help us understand the effects of dark energy, the mysterious energy that accelerates the expansion of the universe. By examining the redshift of light from different distances, scientists can infer how the rate of expansion has changed over time. This understanding of cosmic history not only helps refine our understanding of when the universe began to expand, but also helps put together the complex interplay of forces that will ultimately determine its future. Through the lens of redshift, we grasp the very fabric of the universe's evolution and the story of its vast journey through time. Scientists are detecting and studying primordial gravitational waves, ripples in space resulting from events in the very early universe, particularly processes such as cosmic inflation, with sophisticated instruments and observational strategies. The challenge is that these gravitational waves are incredibly weak and can be easily masked by a host of other signals, including those from nearby astrophysical events. To isolate these primordial signals, researchers are using advanced technologies, primarily gravitational wave observatories and experiments with the cosmic microwave background. Gravitational wave observatories, such as the Laser Interferometer Gravitational Wave Observatory or LIGO and the forthcoming LIGO Australia, as well as space observatories under development, such as the Laser Interferometer Space Antenna, are designed to detect tiny distortions in spacetime caused by passing gravitational waves. While LIGO is primarily concerned with detecting waves arising from black hole mergers, future missions aim to detect waves associated with primordial events. To pick up these primordial signals will require extremely sensitive measurements over broader frequency ranges. Another key technique involves studying the cosmic microwave background, the afterglow of the Big Bang. Gravitational waves can leave an imprint on the polarization of this radiation, particularly through a phenomenon known as B-modes. As primordial gravitational waves stretch and compress space during inflation, they can create specific patterns in the polarization of light in the cosmic microwave background. By studying these patterns with modern telescopes, such as the upcoming Simons Observatory or the already operational Planck satellite, scientists will be able to infer the presence and characteristics of primordial gravitational waves. In addition, theoretical models of cosmic inflation predict specific signatures and patterns of gravitational waves, determining how scientists interpret their observations. By comparing observational data with these models, researchers can distinguish between different inflationary scenarios and measure crucial cosmological parameters. The accuracy of these measurements can help clarify the conditions of the early universe and provide insights not only into gravitational waves, but also into the fundamental physics and mechanisms governing the initial moments of the universe. With these techniques, scientists seek to unravel the mysteries of the formation of the universe, deepening our understanding of both gravitational waves and the evolution of cosmic structures. This research has the potential to rethink fundamental concepts of cosmology and provide a deep understanding of the nature of spacetime itself. The Large Hadron Collider, known as the LHC, is the world's largest and most powerful particle gas pedal, located at CERN, the European Organization for Nuclear Research near Geneva, Switzerland. The LHC, which has a circumference of about 17 miles, accelerates protons and heavy ions to nearly the speed of light and then collides them, recreating, albeit on a much smaller scale, the high-energy conditions that existed shortly after the Big Bang. This facility plays a critical role in exploring fundamental questions about the universe and the nature of matter. One of the LHC's main goals is to study the fundamental building blocks of matter, which are described by the Standard Model of particle physics. The collision of protons at such high energies produces a range of particles, some of which could only have existed at the earliest moments of the universe. By analyzing the particles produced in these collisions, scientists can gain insight into the conditions that existed immediately after the Big Bang, such as temperature, density, and the formation of fundamental forces. The LHC has already made significant contributions to our understanding of the early universe, notably with the discovery of the Higgs boson in 2012. The Higgs boson plays a key role in explaining how particles acquire mass. Its discovery has confirmed theoretical predictions and provided valuable insight into the mechanisms that shaped the universe shortly after the Big Bang. In the extremely hot and dense environment created by collisions at the LHC, it is possible to study the behavior of particles under conditions similar to those that existed in the early universe, allowing scientists to test theories and hypotheses about the primordial state of matter. In addition, the LHC allows for the study of phenomena such as quark-gluon plasma, a state of matter believed to have existed just microseconds after the Big Bang. In this state, quarks and gluons, which are the fundamental components of protons and neutrons, exist in a free and unbound form. By recreating similar conditions in the laboratory, scientists can study the properties of this exotic state of matter, which will help clarify the transition from quark-gluon plasma to hadrons, from which protons and neutrons are formed as the universe cools. Thanks to experiments and results obtained at the Large Hadron Collider, scientists continue to expand our understanding of the fundamental laws that govern the universe, providing insight into the very conditions that created matter and the universe as we know it today. The LHC not only expands our knowledge of particle physics, but also serves as a foundation for broader cosmological theories, connecting our understanding of the smallest scales of matter to the vast cosmos. Neutrino detectors play an important but they interact very weakly with matter, making them difficult to detect. However, they can also provide unique information about the conditions that existed shortly after the Big Bang, especially during nucleosynthesis processes and cosmic events such as supernovae. In the moments immediately after the Big Bang, as the universe cooled and underwent fundamental changes, huge numbers of neutrinos were produced. These primordial neutrinos, left over from that era, are believed to pervade the universe today as a cosmic background, similar to the cosmic microwave background radiation. Although these relic neutrinos are too faint to be detected directly, experiments such as the IceCube Neutrino Observatory and Super Kamiokande has been instrumental in detecting high-energy neutrinos from modern astrophysical phenomena. This gives scientists a glimpse into the processes that took place in the early stages of the universe. When supernovae occur, they also produce a stream of neutrinos in a short pulse that can escape from stellar collapse and travel vast distances in space without being absorbed. By studying supernova neutrinos, scientists gain insight into the dynamics of supernova explosions and the conditions under which they occur. Neutrinos emitted during such events carry information about the nuclear reactions and mechanisms occurring in the core of the exploded star, and thus shed light on elements of stellar evolution relevant to the early universe. In addition, neutrino detectors contribute to our knowledge of fundamental processes such as nucleosynthesis, the formation of light elements such as hydrogen, helium, and lithium, which occurred in the hot early universe. Neutrinos created in that era can affect the rate of nuclear reactions, affecting the abundance of light elements. By studying neutrino interactions, researchers can refine theoretical models of nucleosynthesis and better understand how the elements we observe today were formed. Neutrino physics also intersects with many aspects of cosmology and particle physics, providing a more complete picture of the evolution and composition of the universe. The information obtained from neutrino observations helps researchers to test and refine cosmological models, contributing significantly to our knowledge of the earliest moments of the universe and the fundamental forces governing its behavior. As technology and neutrino detection advances, the potential for new discoveries in this field remains significant and promises a deeper understanding of a universe that is still rich in mystery. The Deep Underground Neutrino Experiment, commonly referred to as DUNE, is an ambitious international scientific collaboration to study the fundamental properties of neutrinos and their role in our understanding of the origin of the universe. Located deep underground at the Sanford Underground Research Facility in South Dakota, DUNE will utilize a vast neutrino beam created at Fermilab, Illinois. This facility aims to study neutrinos produced by intense particle collisions, allowing researchers to explore a number of key questions related to particle physics and cosmology. One of DUNE's primary goals is to study the phenomenon of neutrino oscillations, which describes how neutrinos switch from one type or flavor to another during their journey. This process is critical to understanding neutrino masses and the nature of neutrinos themselves. By measuring these oscillations with high precision, DUNE hopes to gain insight into the differences in mass between the three types of neutrinos, which may also play a role in resolving the matter-antimatter asymmetry observed in the universe. Understanding why there is more matter than antimatter, a mystery in cosmology, is essential to explaining the conditions under which the early universe evolved. Dunn also aims to better study supernova neutrinos. When a massive star explodes as a supernova, it generates a burst of neutrinos that can provide unprecedented information about the processes occurring during the particle explosion. Analyzing these neutrinos will help shed light on the dynamics of supernovae and the mechanisms that lead to the formation of elements, as well as provide evidence of how these events have influenced the evolution of the universe. The experiment is designed to detect neutrinos from both man-made sources and potential future supernovae in our galaxy, allowing scientists to gather valuable data on crucial cosmic events. Dune also plans to explore possible connections between neutrinos and dark matter, potentially looking for rare interactions that could point to new physics beyond the current standard model. Understanding the properties of neutrinos may provide clues to the nature of dark matter and ultimately improve our understanding of the composition and evolution of the universe. Overall, the Deep Underground Neutrino Experiment represents a significant advance in neutrino detection capabilities and scientific research. By addressing crucial questions about neutrinos, their properties, and their relationship to larger cosmic phenomena, Dune will help deepen our understanding of the origin of the universe, shaping the future of fundamental physics and cosmology. Scientists use quasars as cosmic beacons to study the early universe because of their immense brightness and the unique information they provide about the state of the cosmos at significant distances and epochs. Quasars, or quasi-stellar objects, are amazing astronomical phenomena whose energy source is supermassive black holes at the centers of distant galaxies. When matter falls into these black holes, it accelerates and emits huge amounts of radiation, often outshining entire galaxies and allowing researchers to observe them across billions of light-years. One of the primary ways in which quasars contribute to our understanding of the early universe is through the light they emit. When the light from a quasar reaches Earth, it carries information about interstellar space, including the gas and dust in between. By analyzing the spectrum of a quasar, scientists can identify different elements and the states of their ions. This process helps reveal the chemical composition, density, and temperature of the intergalactic medium during the emission of quasar light, which may have occurred billions of years ago during the reionization process that occurred after the Big Bang. Quasars are also a great tool for studying the evolution of the universe. Their immense brightness allows astronomers to observe them from afar and peer into the past. By studying quasars from different periods in the history of the universe, scientists can trace the formation and evolution of galaxies and supermassive black holes. By looking at how the properties of quasars change over time, we can see how quickly stars form and black holes grow throughout the history of the universe. Feedback from quasars is another important area that scientists are exploring. As supermassive black holes grow and run out of matter, they can release energy in the form of jets and winds that affect parent galaxies. This feedback mechanism can regulate star formation, influence the growth of galaxies, and help scientists understand the processes that created the massive structure of the universe. By studying quasars at different stages of evolution, researchers can gain insight into how these interactions contributed to the overall development of galaxies. Studying quasars provides a multifaceted view of the early universe, providing clues about its composition, structure, and evolution through the study of light from a bygone era. With constant improvements in observational techniques and the development of powerful new telescopes, scientists continue to deepen their understanding of quasars, making them invaluable to unlocking the mysteries of the cosmos. Several advanced technologies loom on the horizon that promise to deepen our understanding of the origin of the universe. One of the front lines of research involves the development of space telescopes. The James Webb Space Telescope is already beginning to change the way we view the cosmos, observing distant galaxies and stars in unprecedented detail. Future telescopes focusing on different wavelengths, such as wavelengths or different parts of the energy spectrum, will complement and extend our current capabilities. They help gather information about the formation of stars and galaxies and shed light on the universe's past. Another promising technology is the development of advanced neutrino and dark matter detectors. Neutrinos, also known as ghost particles, are extremely complex and have difficulty interacting with matter. But they can also provide valuable information about cosmic events such as supernovae and processes occurring in the cores of stars. Improved neutrino detectors allow scientists to better detect these particles. They may be able to unlock the mysteries of what happened to the universe shortly after the Big Bang. Quantum computing is also gaining momentum in astrophysics. By processing large amounts of modeling and observational data much faster than traditional computers, quantum systems can help us model complex processes crucial to understanding global evolution. Increased computing power will make it possible to simulate entire galaxies or analyze vast amounts of data from large-scale sky surveys, bringing us closer to confirming theories about the origin of our universe. Finally, planetary and space exploration technologies will play an important role. Missions to Mars, Europa, and other celestial bodies may uncover clues about the building blocks of life and the historical context of our solar system. By studying the geology and atmosphere of these worlds, as well as data collected by various research missions, we will be able to piece together not only the history of the Earth, but of the universe itself. Each of these technologies is a critical piece of a larger puzzle, helping us to unravel the mysteries of the origin of the cosmos.